So today's lesson is about limits where you have either left-hand or right-hand limits or two-sided limits. So far we've just evaluated limits that are fairly easy to evaluate by direct substitution or limit laws. But we're going to talk about functions that aren't necessarily defined by a simple formula. So today's lesson is limits part 3, and we're going to talk about left and right hand limits as well as one-sided limits. So let's start with an example. Let's say we have the function f of x equals, and we're going to do a piecewise function, and if you don't recall what that is, that's a function that has different pieces to it, as evidenced by the title, and there's different restrictions or different qualifications for which area of the graph it's in. So let's say we have f of x equals piecewise function of 3x minus 4 only when x is less than or equal to 2, and x plus 6 when x is greater than 2. So let's go ahead and sketch the graph of this. And if you're not sure how, just take it, no pun intended, piece by piece. So let's start with the linear function, because that's slightly easier. So x plus 6 is a straight line, but only we want to look at when it's greater than 2. Sometimes it's helpful to start at 0. So if we plugged in 0, well 0 plus 6, is positive 6. We need to start greater than 2. So let's start at 3. Actually, let's start at 2. So if we plug in 2, we get 8, positive 8. So at 2 we get 8, but because it doesn't equal 2, let's put an open circle and then a straight line afterwards. Okay, I don't really need to know what 3 is. I could plug in 3 and know that it's 9, so actually let's draw this a little bit more accurately. This is 8, positive 3 is 9, so our sketch needs to be sort of accurate, but we know that it's a straight line going to the right. And we know there's an open circle at positive 2 because x does not include 2. Now let's talk about our quadratic function, and that occurs only when x is less than or equal to 2. So if we were to think, let's make a table of values, it usually helps. So let's plug in 2, 1, and 0 and see what our graph looks like. So we plug in 2 here, we get 2 squared, which is 4. So we get 12 take away 4, which is 8. So at 2, we actually get an overlap, and we can now fill in this circle because this quadratic function does include 8. At positive 1, we get 3 times 1, which is 3, times minus 4, which is negative 1. So at 1, we have negative 1. And at 0, we have 0 minus 4, which is minus 4. So that's actually our y-intercept. Now, I don't see a quadratic yet, so maybe let's take one more value to see if we can find that curve we're looking for. So if we take negative 1, we will also get negative 1, and that tells us that we've now started to see our curve. So we know a quadratic looks like that, and we've now sketched our piecewise function. So the piece from negative infinity to positive 2 is our quadratic, and the piece from 2, not including 2, to infinity is our x plus 6, our linear. So we call this a piecewise function. Now, when we take the limit of a function like this, and we're going to be approaching 2 because that is the special point where the graph changes. So when we take the limit of f of x for this function, we have to look at it from both sides of the graph. We have to look at it from the left-hand piece, and we have to look at it from the right-hand piece. So let's leave this example for now. Leave yourself a little bit of space And let's talk about the definition of a left hand and a right hand limit. So a left hand limit. So the limit as x approaches c, some constant, from the left hand side, notice the notation is a negative, of f of x equals L. And this means that when x is near but on the left side of c, on the negative side of c, not necessarily negative on the x value, but on the left side of c, then f of x is near L, the left-hand limit. We can say in the same vein that the right-hand limit let's just say left-hand limit and right-hand limit. We can say the limit as x approaches c from the positive side, from the right-hand side, equals L, means that when x is near but on the right side of c, then f of x is near the limit. Okay, and this brings us to the theorem of two-sided limits. This theorem says that if the limit of x as it approaches c on the left-hand side of f of x equals L, if this equals the limit as x goes to c on the right-hand side of f of x, then the limit as x approaches the constant, notice not from the left or right, but just the constant, then the limit of f of x equals L. However, if this is not true, then the limit as x approaches c of f of x does not exist. And a shorthand way of writing does not exist, of course, is DNE. Does not exist. So just to recap all of that, a left-hand limit means that when x is approaching a constant from the left-hand side, and it approaches f of x, it will equal a value L. The right hand is if a limit approaches a value c from the right-hand side and it equals L. And the theorem of two-sided limits states that if the left-hand limit and the right-hand limit are equal, then the limit exists at that constant c, but if they do not equal, then it does not exist. So if we go back to our example at the top, if we take the limit of f of x as x goes to 2, let's take the limit from the left-hand side and the right-hand side. Okay. So we take the limit as x approaches 2 from the left-hand side, and we're going to take the limit as x approaches 2 from the right-hand side. Now, there are two different functions, so how do we know which of these is the left-hand side and the right-hand side? Well, this is why we sketch the graph, because it's helpful to see it visually. So we can see that here is 2, and to the left of 2 is our quadratic function. So if we do the limit as x approaches 2 from the left-hand side, we're talking about 3x squared take away 4. And if you hadn't drawn the graph, you could have looked at your piecewise function here and seen that this was x is less than 2, so on the left-hand side, and this is where it's greater than 2, so that's on the right-hand side. And when we evaluate this, the limit as x approaches 2 from the left-hand side, we get 3 times 2 squared take away 4, which equals 2 times 2 is 4 times 12 take away 4, which is 8. And the limit from the right-hand side of x plus 6, when we evaluate, we also get 8. So we can say that therefore, the limit as x goes to 2, not from the left or right, but as it approaches the value 2 of f of x equals 8. And we can see that on the graph. As the graph approaches 2 from the left-hand side, it approaches 8. And as we follow the linear function closer to 2, it also approaches 8. So let's do an example now where there's a hole in the graph and see what happens. So let's talk about what happens when we have a hole. So here's example number 2. Find the limit as x approaches 3, so let's do 2, of f of x, where f of x equals where f of x equals 9 take away x squared, where x is less than or equal to 2, and 4, where x is greater than 2. So here's our piecewise function. So we can sketch the graph, or we can just try to evaluate before we start. So let's sketch a graph, because it's always better to visually see what we're looking at. Alright, so if we sketch the graph of 9 take away x squared, we know that that's a parabola with a vertex of 0, 9, and we know it is going down and goes through 3 and positive 3. And if you don't know how we got that, recall that 9 minus x squared is a difference of squares, and to factor that we would say 3 minus x times 3 plus x, and that gives us our intercepts. So we have an intercept here and an intercept over here. But our graph stops at 2, so let's plug in 2 into our quadratic. So 9 take away 2 squared would give us 5. And let's color in the dot, the point I should say, because it is included. So we've got our quadratic, but it stops at 2. And then let's talk about our function of 4. So no matter what we plug in for x, we always get 4. So 1, 2, 3, 4. At 2, our graph starts at 4, and it always continues as 4. It's always equal to 4. Now notice what happens. We have a gap between 4 and 5, which means that this is really a piecewise function. There's a piece over here, and they actually don't connect. So we can take a guess that when we evaluate the limit at 2, it is not going to exist. So the limit as x approaches 2 from the left-hand side of f of x is equal to the limit as x approaches 2, and the left-hand side of our graph is the quadratic function. Or if you look over here, x is less than or equal to 2, that's the left-hand side of our graph. So it's the limit of 9 minus x squared. When we plug in 2, we get 9 take away 4, which equals 5. The limit as x approaches 2 from the right-hand side of f of x would be our function 4. And we know that when we take the limit of a constant, it equals the constant. So what we can say is, therefore, because the limit as x approaches 2 from the left-hand side does not equal the limit as x approaches 2 from the right-hand side, the limit as x approaches 2 of f of x does not exist. So it is possible for a limit not to exist. If they approach different values, there's no way for that limit to exist.